I just learned that Trevor Hasty, who's one of the authors, calls it GLMnet, and I've never heard it called that before. So, it saves a few syllables. But anyway, I'm going to talk to you about Python implementation of elastic net regularized generalized linear models. So I know that's a mouthful, and I'm going to be spending most of this talk unpacking that title. Okay, so first I'm going to tell you about linear models, and then how to generalize linear models, and then say a few things about regularization, and then talk to you about a specific form of regularization called elastic nets. But before I move on with I just want to note that in data analysis and data science, we live in a continuum of ideas, and there's something of a trickle down where you have algorithm developers like Hasty and Tipshirani, who are the authors of GLM and inventors of elastic net, and then you have software developers like the scikit-learn guys, and then you have practitioners who use these to apply to a wide range of insights. And so I'm going to assume, the way I've structured this talk is to assume for that we don't have scikit-learn. Let's say there's an apocalypse and tomorrow everything is the same except we don't have scikit. So with that in mind, I'm going to talk about how we can sort of DIY our own GLMnet. Okay, so generalized linear models. Pardon? Oh, okay. Do you mean the text there? Well, so that's not meant to be read. Just read the title. So this is just a screenshot of Google Scholar search for generalized linear models. This is something that's existed for over 40 years, and generalized linear models are generalized versions of special cases like linear regression and logistic regression. And I just put it out there to tell you that it's been cited over 5,000 times. So it's a very versatile and popular tool for data analysis. Fast forward a few, and you have net, which is an algorithm for regularizing these models. I'll tell you what regularization is in a minute. But again, you can see that's extremely popular and has close to 5,000. You also have a very robust package in R, which has close to 3,000 citations. All of these are widely used tools. If you look at the special cases of generalized linear models, you have only normal, so linear regression and logistic regression that's available in scikit-learn with elastic net regularization. But often you have problems where you need to do Poisson regression or multinomial regression or Fox regression, for which we don't have tools in Python. So Pyglmnet aims to address that gap. Okay, so why is it that I built Pyglmnet? So I'm a computational neuroscientist, and I thought because it's PyData, I can show you on PyDay. So this is where I work with a bunch of other computational neuroscientists. And in our day jobs is we want to understand how the brain works, and in particular, we want to relate what happens in the environment and behavior to brain activity. So a tip like this, we have a lot of collaborators. And so when we put a monkey in the lab and we showed some environmental stimuli, in this case a visual stimulus, but the monkey can also control a joystick which controls the cursor on the screen. So when it moves the joystick, the cursor can move on the screen, and so we give it a bunch of tasks. The actual details of the tasks are not that. We have a quantification of the environmental stimuli, so features from the visual stimuli, and then we also record its movement, of its behavior, and we want to neural activity. And to be specific, the types of neural data that I work with are spike trains. So when we record from the brain, we record voltages from the extracellular matrix in the brain. And so each spike is a discrete event. It's a change in voltage event through which in the brain communicate with each other. So the most standard way to do neural data analysis is to take a narrow time window of interest, like you see in the little box there, and you count the number of spikes. So we have all kinds of features, and we want to use those features to predict count data. And count data is best modeled as Poisson process. So we also have count statistics in the real world, and to give you a more germane example, we all develop software and contribute to GitHub repositories, and sometimes we wonder why certain repositories have more stars than others. And so if we want to build a model, we have to predict a target variable that's measured as a count, and so we can model that with Poisson regression, right? So we can imagine a bunch of features that we want to use to predict this model. So let me give you a concrete example of the data that we work with, going back to, these are a couple of example neurons. Oh yeah. Okay, can you hear me clearly? That's Is that better? Is that better? Okay. Okay, so going back to a couple neurons, you see spike. What you see here on the y-axis are spike counts, and on the x-axis is arm. What you see here is, in this particular neuron, you don't have that much variability, but in this particular neuron, the nature of the variability is nonlinear. Right? So if you use vanilla linear regression, you're going to get a bad fit to the data, but also linear regression is not going to be able to predict spike counts that always have to be positive. And instead, if you fit a Poisson regression, you're able to capture the nonlinearity in the relationship between velocity and spike counts, but you're also able to ensure that the prediction is always positive. Furthermore, generalized linear models, you can sample data from once you fit the model, and you can see that if you draw samples from a model that's been fit, you see that the sample data and the true data have a much better match for the Poisson regression. So without going into the details, this is just KL divergence is a way to compare two distributions, and you can see the divergence is much smaller. Okay, so this is just to motivate you the importance of Poisson regression for people like us. Okay, having said that, I want to kind of start with the math and walk you through how we go from linear regression to generalizing linear regression. So most of you have encountered this in previous talks. So in linear regression, you have a bunch of predictors. Let's say you have p predictors, and then you have a target variable y. And so when you want to build a model, you go out there and collect observations. So let's say you have n observations. And you can write that out in matrix form as y hat, which is a prediction, is some bias term, beta 0, plus a matrix of your observations times predictors, n by p matrix, multiplied by the weight vector that you want to estimate, beta, right? So you can write that in 2 lines of Python code. With NumPy, you can just do a matrix multiplication with x and beta, and then add the bias term, and that's your predict function, right? So now you want to estimate these, and the most standard way to estimate these parameters given the data is to use something like a mean squared loss. And many of you are familiar with the mean squared loss, so I'm just writing that out here, where you have the prediction y hat and the true data y, and then you take the square and you take the mean of that, sum of that, you take the mean, and then you can write the same out in matrix form as an inner product between the error and itself, right? And so you can see that that's a loss function that we can then optimize to estimate the parameters. And so I define the loss function in 3 lines of Python code. You compute the prediction, and you compute the error, and you compute the inner product of the error with itself, and that's your loss function. So before I proceed, does anybody know why we use the mean squared loss for linear regression? Yeah, it's convex. It's easy to estimate, but also the mean square loss is the negative log likelihood of a model which has normally distributed noise. So you can write out the same linear regression in a probabilistic form where you assume that in addition to the model, you have some random noise, and the noise can be normally distributed. So this symbol here just tells you that you have some normally distributed noise with zero mean and some diagonal variance. And so given that model, you can write out the probability of observing your target variables given the predictors. And so this is just the PDF of the Gaussian distribution. So you have an exponent term and you have a term within the exponent. This is the PDF, and I'm just leaving out all the aspects of the PDF that don't depend on the betas, right? So given that you have a number of observations and assuming that each of those observations are independent, you can just multiply all those probabilities together, and that's where you get this product from, right? So this is the likelihood of observing the data, given the predictors. And if you take the log of this and the negative of the log, you see that it looks exactly the same as what we saw here, the mean square loss, right? So the mean square loss is the negative log likelihood loss, and we're going to use this simple idea to generalize from linear regression to generalize linear models. Okay, so again, for linear regression, this is the model, and you can just rewrite that as the target variables y being normally distributed with a mean function which is given by the linear regression model, and some diagonalized variance, right? So this is a special case of generalized linear models. So what do we do to go from linear regression to GLMs? We take this normal distribution and we replace that with a more general form. Normal distribution is just a special case of a distribution in the exponential family, right? So you can replace the normal distribution with an exponential family that has some mean function and some other parameters, right? The other thing that you do is you can add a nonlinearity. So in linear regression, you just have a linear term, but here you can, on top of that, you have a pointwise nonlinearity over the linear term. So you literally do two things to go from linear regression. You add a pointwise nonlinearity and you change the noise distribution, right? So we'll see a special case of this, and we can go back to Poisson regression and we'll see how what those two assumptions are. You make those two assumptions and you get a special case, right? So in the case of Poisson distribution, we assume that the nonlinearity is an exponential, right? And you can just rewrite the predict function by adding an exponential term here. That's it. And then we can also assume a certain noise distribution. So you assume that the yi's are Poisson random variables with a mean lambda, where the lambda is modeled by this nonlinearity, right? So with these two assumptions, you can now write out the same loss function that we wrote for linear regression. You can write out the negative log likelihood, right? So this is the PDF of the Poisson distribution. You can write the likelihood, and it's going to look like that. You can remove the parameters that don't depend on lambda, and then you take the log of that, and you take the negative, and so this becomes your negative log likelihood, which is the loss function, right? So you can rewrite your loss function for this special case of Poisson regression. Essentially, I'm just writing two lines of code to say sigma I yi log y hat minus yi hat, right? And that's your loss function here. And you can do this over and over again for different special cases, but in the interest of time, I'll just leave these on the slides and move forward. Okay, so just to recap, we've defined linear regression. We've defined what GLMs are by making those two assumptions about nonlinearity and noise distribution. Now we need to estimate the parameters, right? So in every single machine learning model that you have looked at through the conference, or any machine learning model that you use, you always have to do optimization to find the parameters that minimize the loss function, right? So if you recall your calculus 101, in order to find the minimum of a function with respect to some parameters, you take the derivative and you set it to 0. So let's do that for linear regression, right? You take the derivatives, you set it to 0, and you get a system of equations. So let's say you have p predictors and one beta term for each predictor. This is going to give you a system of p linear equations, right? And it so happens that for linear regression, this derivative is linear in beta. So this is a whole set of linear equations, and you solve those linear equations, and you get your optimal estimates beta and beta 0, right? So you can just write a function to calculate these derivatives. We call them gradients, and this is like a little piece of code. So you just it's really just the error term and the matrix product between the transpose of your predictors and the error term, and so you can write that out, right? Now you can do the same for another case, logistic regression. I won't walk you through all the math here, but I just want to point out that this is no longer a linear equation. This is a much more complicated form, and so you don't have a closed form solution. So when you have a system of linear equations, you can easily compute a closed form solution, but you can't do that in all special cases, right? But you can still write out the gradient of the loss function, just as we did here. You can write out the gradient, right? So if you can't compute the solution in closed form, how do we optimize it? Anybody want to take a guess? It's gradient descent, right? Gradient descent is really the core engine behind every optimization algorithm. And so what do you do in gradient descent? You say, oh, I don't know what the right solution is for the minimum, but I'm going to take a guess. I'm going to start from a starting point, right? So let me guess that this is an example. It's just like a quadratic function that you want to minimize, but I'm going to guess that my initial solution is there. So then I compute the gradient, and the gradient in this case is just the derivative, which looks like this tangent function, right? And so you can see straight away that you see that this tangent is pointing downward, so the slope is negative, right? So this is going to be a negative term. This is going to be a negative term, right? And then you have something called a learning rate, where you decide how far to make a step in the direction against the gradient. That's why you have this negative sign. So you're going to move, this is a negative term, and you have a negative sign, and you're going to put those two together, and you're going to move in a positive direction. So let's make one update, right? You make an update, and you move the solution closer to the minimum. You do the same thing over and over again. You make 5 updates, you make 15 updates. By the time you do 50 updates, you've converged at the optimal solution. So that is gradient descent, right? So this is the fit function that you call for your scikit-learn algorithm. If you were to write a fit function for an estimator, this is what it would look like. Okay, so this p is just, it's telling you how many predictors there are, and you can get that from your x. And then you initialize your parameters to some random initialization. Make sure you normalize them to have, to sum up to 1. And then you iterate over a finite number of iterations that you can pass as a parameter. And then in each iteration, you compute the gradients. So remember, we wrote these gradient functions in the previous slide. And then you just take a step along the direction of the gradient in each iteration. And once it's done looping through, you return the best estimate, right? So that's it. In 5 lines of code, you have the fit function for gradient descent for a wide range of models. Okay, so we're almost done. We're halfway through the title. We've defined linear models, generalized linear models, but now we need to understand what elastic net regularized is. Okay, so regularization is the idea that if you have finite amount of data, but you have a large number of predictors or features or hypotheses or whatever you want to call them, you're going to do exceedingly well on predicting that finite training data. But then if I give you some new samples of test data, then your prediction is going to be poor on the test set, right? So the idea of regularization is that, let's say you have 2 different models, one with P predictors and one with Q predictors. So if Q is much larger than P and it's just subsumes all these predictors, then in general this is going to do much better on your training set. And therefore you need to make sure that you penalize a more complex model in some way. So the idea of regularization is to just add a penalty term to your negative log likelihood loss function. So instead of minimizing just that log likelihood, which measures the goodness of fit of your model to data, right, you add a penalty term. And the most classic penalty to use is to take the sum of squares of all your weights. And the idea of and this is called L2 regularization, and so this loss function is called the L2 penalized loss function. It's also called ridge regression, it's called different things in the literature. But you add this penalty term and then you repeat the same thing. So you can define the L2 loss function and you can compute the gradient of that. You already have the gradient of the loss, and to that you just add the gradient of this term, right? And then you're done. Once you have the loss function, the gradient, you know how to write the fit function because you just have your gradients and you update them at each iteration, right? So let's actually take some simulated data and look at what happens when you do and when you don't regularize, right? So when you add this penalty term, you have a parameter called lambda, and that's called the regularization parameter. So let's see what happens when lambda is extremely large, right? The loss function is dominated by this term. And when lambda is extremely small, the loss function is dominated by this term. So when it's dominated by this term, it cares only about fitting to the training data. But when it's dominated by this term, it doesn't care about the fit at all, and it's just going to push all your parameters close to zero. So what we do in practice to estimate lambda is we take the training data, we split it into a subset, and then a sub-training set and a validation set, and then we sweep through a range of lambdas to find what the best lambda is. And so what you see on the left here is a plot of the goodness of fit, like a score function or an R-square, of the training data and the test data, the training data in red and the validation data in green, against the values of lambda. So, and this is a logarithmic scale. So you see for very small values of lambda, you get a really good fit to the training set. But then when you show it the validation set, it does pretty poorly, right? So this gap between these two curves, the red and the green curves, is a measure of the extent to which your model overfits the training data. But then as you sweep through the lambdas, you increase the lambdas, your prediction on the red curve is going worse. On the training set is getting worse, but on the test set is getting better. So you want to stop and choose the lambda at which your prediction on the validation set is the best. And so this is called cross-validation, and you do this all the time to select your optimal regularization parameters, right? Well, how much time do I have? Oh, so this is good for problems where you have a large number of you have a lot of data, but also a large number of parameters. And here you see that in black, you see the different parameter values, the true beta values, and in red, you see the estimated beta values. So you see that because of regularization, the estimated beta values are kind of pushed closer to zero, right? So this is nice to have because you don't want to weight something too heavily and risk overfitting to your training data. But it's not so useful in scenarios where you have a large number of hypotheses, a large number of predictors, but only a small number of them are actually useful in the prediction problem. And this happens all the time in biology. So if you look at problems in genetics, for instance, where you have your measurement of 5,000 genes, let's say, but only 2 or 3 of them are relevant to that particular cancer type. So that's called a sparse scenario where you have only a few predictors that matter for your problem. Then you don't want to use something like ridge regression. Instead, a very common technique is called lasso regression or L1 penalty, where what you do is you take the absolute values of the weights, and then you add that as the penalty. Instead of the squared term, you take the absolute values. So what this does is something very different. So instead of uniformly pushing all of the weights to zero, penalizing by using this absolute value makes a lot of the weights go to zero and leaves very few weights to be non-zero, right? And so you can define your, as before, you can define your loss function like that a single line of code. But let's go back to our example and compare the difference between ridge regression and lasso regression in an example, right? So you have 200 observations, but you have 500 predictors. And what you see up on top is the same figure that you saw earlier. In red is the goodness of fit, or the R square, on the training set, and in green is the goodness of fit on the validation set. And you see that ridge does really poorly because it continues to, even though you increase lambda a lot, it continues to fit very well on the training set, but extremely poorly on the validation set. And so the gap between these two lines is still very large, even as you increase lambda a lot, right? But by comparison, you see the same figure for lasso regression, and you see that these curves meet already when you have a modest value of lambda, right? So lasso regression is much better in scenarios where you have only a few non-zero weights. So again, what you see here in black are the true weights, the true parameters of the model, and in red the estimated parameters. So here you can see a clear failure mode of ridge regression where most of the weights are like squashed to zero, and it's not really doing a good job of generalizing. But by comparison, you see the red dots here, and most of them are set to zero, but it still correctly identifies a couple of the parameters. In fact, a couple of the parameters that are most important in the prediction, it correctly identifies those, and so it's able to generalize fairly well to the test set, right? Okay, so that was a preamble about regularization, ridge regression, and lasso regression. Now I'm coming back to the title of the talk, elastic net. So elastic net is kind of a nice way to interpolate between the advantages of ridge regression and lasso regression, right? So all you do is recall that in ridge you had the squared loss, and in lasso regression you had the absolute loss. And so you say, oh, I don't exactly know how much I should use these two, but I'm going to use another parameter called alpha, which is sometimes known as the L1 ratio. So you say, I'm going to weight this L1 loss by alpha and the L2 loss by 1 minus alpha, and that's your elastic net penalty. And so you add that penalty to the negative log likelihood, and you get your elastic net loss. Again, you can write that out in the same way. And so once you have your loss, you have your gradient of the loss, you can go back to your fit function and do the same gradient descent and solve it, right? So at this point, I should say, that's it. The talk is done, right? But if you go and look at the R package, there's a bunch of different tricks that they use to make the technique work, and some of this actually comes from fairly advanced optimization theory. So at this point, I just want to check how much time I have. I still have 15 minutes. Great. So maybe I can pause for a minute or 2 minutes to take questions before I proceed with advanced optimization techniques. Mm-hmm. Yeah, that's a really good question. So there are at least two different ways to interpret that. One of them is that you're doing something Bayesian here, which is, if you have the likelihood, you have the negative log likelihood, you don't really make any assumptions about what the parameters should look like. But the moment you add a penalty term, any penalty, okay, so you can think of that penalty as a prior on the weights. So when you actually go back, so this is the negative log likelihood, right? So when you take this entire term and you go back from negative log likelihood to likelihood, you're going to see that it's actually a product of two different probability distributions. And it turns out that this probability distribution is going to correspond to, let's say in linear regression, is going to correspond to the PDF of a normal distribution, right? But if you take this probability distribution, it's going to correspond to prior on the mean of the probability of the normal distribution, right? So if you use a squared loss, you're using a normal prior. If you use the absolute loss, you're using what is called a Laplacian prior. And what does a Laplacian prior do? It selects, a Gaussian distribution looks something like that, right? A Laplacian distribution looks something like this. So you can think of it, they sometimes call it stick and slab prior. So you have a stick that's close to 0, you have a lot of probability mass that's close to 0, and you have long tails. So you're going to have very few values, low probability mass, but still greater probability mass at the tails than a Gaussian distribution, so that you can get very few large values, but you're going to get most values very close to 0. So that's a Bayesian interpretation of regularization. Do you have any other questions before I proceed to the advanced optimization techniques? Is that all making sense? Gradient descent, regularization. Great. So I'm going to tell you about 4 tricks that these aren't really tricks. They're actually very theoretically grounded things, but it's not taught in optimization 101 class, and so I really had to spend a lot of weekends and nights digging through these papers before I figured them out. But if you look at this term, right, the absolute value, recall that when we do gradient descent, you have a loss term, and then you have to compute the gradient with respect to the loss. This absolute value function is not differentiable at 0, right? So if you have a function that's not differentiable at 0, or it's not differentiable everywhere where you're interested in, how do you take the gradient, right? So that's the first trick that they use. They use a technique called projected gradient. So in projected gradient, what you do is you take the gradient of everything else except this term, which you cannot differentiate, and then you apply what's called a projection operator. So you do the gradient update as always, and then this projection operator, what it does is it does something called soft thresholding. So if you have a projection function of x with respect to some threshold called lambda, is basically you take the value x if the absolute value of x is larger than lambda, or if it's smaller than minus lambda, then you shrink it by lambda. So you basically shift it towards 0 by lambda. So you do this, and then if it's larger than lambda, you do that, but if it's smaller than lambda, you push it down to 0 already. So that's called the projected gradient, and I won't get into the theory of why that works, but it's a pretty simple technique, and you do that after every update step, and it guarantees convergence, right? So, and the way to implement that in Python is you just define the soft threshold function, and then instead of doing the typical gradient descent update where you take the learning rate times the gradient, you also push it through this proximal operator. Right? So that's just one line of code that you need to change in your fit function. Right? Okay, that's one trick. But as a result of this trick, you can do a lot of other cool things. So one of the things that you do is you typically sweep. I recall that in regularization, I said you can sweep through a range of lambdas, right, and select your optimal lambda. So that's called the regularization path. But in practice, what they do is something called warm restarts. So they select the largest value of lambda, which is going to push the majority of the weights down to 0, and then they initialize subsequent solutions for the next lambdas with the optimal solution for the previous lambda. And what that does is it dramatically speeds convergence, because you're starting with an extremely good guess of what the solution is going to be. So that's called warm restarts, and that's again pretty easy to implement, because you just store like a dictionary of your solutions from the previous value of lambda, and then before you start your optimization, you just initialize with the previous value of lambda, right? So that's another trick. The third trick is also really interesting, and it also speeds up convergence. It's called the active set trick. So recall that in the projected gradient method, if you have small values smaller than lambda, you're going to push them down to 0, right? So what the active set technique does is maintains an active set of all the lambdas that are non-zero. And then at each iteration in your gradient descent, you only update the non-zero terms. So imagine that if you have a set of 1,000 predictors, right? Now, in a typical lasso problem, elastic net problem, you're going to have maybe 800 of those are 0. So So already in the first iteration, if you identify maybe 700 of those get pushed down to 0, you only need to update the remaining 300. So the number of iterations required for convergence becomes dramatically faster, because in each iteration you throw away the values that are already set to 0 and you only update the non-zero values, right? And the final trick is to do something better than vanilla gradient descent. So because a large number of values are getting set to 0 by things like active set and soft thresholding, you can actually cycle through the updates, the parameters one parameter at a time. So recall that in gradient descent, if you have 100 parameters, you compute the gradient with respect to all the 100, and then you make one update step across those vectors, right? But in coordinate descent, what you do is you cycle through all the coordinates one coordinate at a time. And again, this is much faster because if you have an active set that's rapidly shrinking from like 1000 to 300 to 30, then you only have to do that many cycles of your coordinate descent, right? So they do that, and the other thing that they do is to use a Newton update. So a Newton update, I don't want to, in the interest of time, I'll skip exactly what that is, but I do have a notebook on the repo that you can go to try and understand the difference between vanilla gradient descent and Newton update. But what Newton update does essentially is gradient descent only tells you the direction in which you want to update. You have to still assume a learning rate, right? In Newton's method, you can do much better than just guessing the learning rate. You can actually get a much better estimate of how much to move depending on the local curvature information in your loss function, right? So they use Newton's method as well in cyclic coordinate descent. So I think I'm coming to the end of my list of tricks that Tipshirani and Hasty have used to speed up the R package, and all of these are implemented now in the Pyglmnet package. The only thing that remains to be done is to translate some of the most critical components from Python to Cython, and it's something I'm actively working on. But before I conclude, I wanted to say that in optimization and machine learning, we work a lot with gradients, so we work a lot with calculus, and all of the differentiation, the matrix differentiations that I've told you about, I've done by pen and paper on a whiteboard, right? But you can also take advantage of symbolic differentiation packages that Python gives you. So there's a package called SymPy, which is like Mathematica. For some of you might have used Mathematica. But here's like a little snippet of code. I have more details on the SymPy notebook. But what SymPy in essence lets you do is lets you initialize symbolic variables, right? And then it has functions like diff. So you initialize your symbols x1, y1, x1, x2, y, beta 0, beta 1, beta 2. This is like just a toy problem to illustrate SymPy, right? And then you have your prediction, and you compute the loss. There's no computation going on here. These are all symbolic variables. And then when you do the differentiation, you also have like an additional simplify function that just kind of cleans up your algebra. You can do that, and then it just gives you what the derivatives should be. And you can kind of use this to check your math, right? So like I have like a linear regression example, logistic regression example. You can walk through it on the notebooks. So that's one advantage of SymPy. But of course, Theano is also our friend, and we have advanced tensor libraries like Theano and TensorFlow, which do one better. They don't just let you check your math; they take away the job for you and do it for you. So that's called automatic differentiation, and it's a very old field, but it's become extremely mature in libraries like Theano. And so I've just re-implemented linear regression in Theano in these slides, and I'm just gonna leave them here, and you can look through the Theano notebook. But I'll briefly point out it's essentially a similar idea to SymPy. So you have symbolic variables that you initialize, and then you can do all your operations symbolically, right? You initialize shared variables for your parameters that you update, and then in just these two lines of code, you've defined your GLM. So what does this line of code do? It computes the prediction. This is like the predict function, and then this is the loss function, right? It's just these two lines of code. But the amazing thing about automatic differentiation is you don't have to write gradient of the loss. You don't have to write a function for it. You just say theano.tensor.grad, and you say I want to compute the gradient of the loss with respect to these beta 0 and beta. And that already gives you symbolic gradients, right? So it's just these two lines of code. If I want to implement logistic regression, I just have to change the predict function, and I have to change the loss function, change this to the logistic loss, and that's it. I'm done. So Theano can, and then you compile this, and then you fit the model and you predict it, right? So you just have like two compile functions. One is called fit and the other is called predict. And you just simply tell it that, this is my data x and y, and these are the things that I want the function to return, the prediction and the loss. And in each step, I want you to update the parameters according to the gradients. So in 5 lines of code, Theano can do all the work of the fit and the predict function, right? And actually, if you're interested in automatic differentiation in Theano, there's a library called sklearn Theano, which is re-implementing some of the most useful scikit-learn functions in Theano, and that's something you can go take a look at. But yeah, Theano is a very mature library, and it's fairly easy to use, although I hear that the error handling is not, the error bug reporting is not as good. But it's a really powerful library for automatic differentiation. So that concludes the theory part of the talk, and I just want to briefly say that you can go look on the repo, but it's all object oriented, and all the methods live in one single class called GLM, and all of the doc strings conform to the doc string, which gives you the help for the class, and the methods all conform to scikit-learn standards. So you have all the parameters. I think you have like maybe 10 or 15 parameters for the class. There are fit and predict and score methods, just like for any estimator in scikit-learn. And there's also a simulate method that is convenient for drawing samples from the fit models. And then the other advantage is, since we always fit this in a regularization path, sweeping through the lambdas, you can also slice the estimator. So if by default it fits through for a default range of lambdas, and so if you want the prediction for one particular thing, you can just slice it, say model GLM0.predict, right? But anyway, I won't bore you with the implementation details and the API details. There's a good documentation page. And this is the URL. You can go take a look at the documentation. And pretty much all the math that I told you about in the talk is available in the tutorial. There's also a small example gallery that demonstrates how the APIs work, how the benchmarks with respect to Pyglmnet and scikit-learn, certain scikit-learn implementations, some benchmarks between Pyglmnet and R. All of those, we're starting to add those. And there's also a little bit of developer documentation if you want to help me, because I'm pretty much the developer team here, except for a few friends who pitched in. And so you're welcome to look at the developer documentation, contribute. And so I think I'm going to summarize. So we learned that the mean square loss is a special case of the negative log likelihood. And then we learned that we can define GLMs by just going from linear regression and assuming a non-linearity and assuming a noise model. We learned about regularization, and we learned about how to define elastic net as a combination of ridge and lasso regression. And then we learned about optimization techniques using gradient descent and all kinds of other advanced optimization tools that Hasty and Tipshirani use in the GLMnet package. And finally, remember that SymPy and Theano are really useful and powerful tools to make sure you don't get your calculus wrong. So I'd like to stop here. You can go check out the slides in the notebooks there on the repo. You can clone the library, start playing around, applying to your data, and go look at the issue tree, post feature requests, and contribute. Thanks a lot.
We would take one question. Okay.
And it marks up you implementing stochastic gradient descent
Yeah, that's on the cards. Yeah, especially if we want to scale up to large data sets, I think it'll be good to use stochastic gradient descent. I mean, my first step is I want to evaluate whether Python versus Theano is going to give me the best in terms of speed up. Because if I choose to use Theano, then all the stochastic gradient descent methods are already implemented in their optimizers. So